All right, I suppose it's time to begin. So we'll start off talking about trapezoid and Simpson's rule. So what I would say mainly is that the point of these rules, I guess, the point or the main purpose of these rules is to allow us to approximate the value of a definite integral where we wouldn't be able to use the fundamental theorem of calculus part 2. Where we could not use FTC part 2. A couple examples of this would be something like, famously, the integral from 0 to 1 of e to the negative x squared. That is a function that does not have an antiderivative. Or we say it doesn't have an elementary antiderivative, meaning you can't write it as normal functions added, subtracted, multiplied, divided together. You can write it as that. That's the antiderivative of the negative x squared. Look, there it is. But it's not very helpful. Another example would be the integral from 3 to 7 of 1 over the natural log of x dx. That's another function that does not have an antiderivative. There's a lot of functions that don't have antiderivatives that we can find nicely. We don't do a lot of exploring of them because we can't find their antiderivatives. But let's go ahead and use these techniques on functions that are a little bit easier to actually evaluate. So we're going to apply these techniques, rules, whatever you want to call them, to some easier functions, just for the sake of being able to actually calculate things. So let's look at some examples. And again, as always, if you have questions, please ask, and I'm happy to clarify things or answer other questions. Let's approximate the integral from 1 to 3 of 1 over x dx using the trapezoid rule with n equal to 4 trapezoids. So let's draw a picture. Actually, before we draw a picture, I'll just point out that the actual value of the area under the curve we could calculate. So note, the integral from 1 to 3 of 1 over x dx is in fact equal to the natural log of x evaluated from 1 to 3, which is going to be the natural log of 3 minus the natural log of 1. The natural log of 1 is 0, so that's the natural log of 3, which is approximately 1.0986. So our answer should be reasonably close to that. So how are we going to approximate the answer using the trapezoid rule? Well, let's draw a picture. So here is my xy coordinate system, and I'm going to draw the function y equal to 1 over x. And I'm going to identify my intervals. So my intervals from 1 to 3. It's a little bit exaggerated on the y-axis. That's okay. So there's the, I should say. So all that area under the curve, f of x equal to 1 over x, from x equals 1 to x equals 3, that's what we're trying to approximate. And what we're going to do is we're going to break this region up into 4 equal width subsections, and then find the area, or I should say approximate the area of each of the subsections using trapezoids. This is kind of like, in fact, sometimes this gets taught way earlier in the quarter. This is kind of like way back when we were doing Riemann sums and breaking up the integral into some equal number of subintervals and then approximating each area by using rectangles. Now we're going to use trapezoids instead because they give a slightly better approximation. So I'm going to break this up into n equal to 4 subsections. So that means each subsection has a width of delta x equal to the entire width, which is 3 minus 1, divided by 4, which is 2 divided by 4, which is 1/2. And then we're going to break this up into 4 sections. So the endpoints of my sections are 1, and then 1 plus 1/2 is 3/2. 3/2 plus 1/2 is 2. 2 plus 1/2 is 5/2. 5/2 plus 1/2 is 3. So each of these subsections is a width of 1/2. And then we're just going to draw the trapezoid. So check it out. And here's my best attempt to draw this. If I actually draw this trapezoid, it's going to be that shape right there. And then similarly for this next one, I'm just really connecting the tops of the functions right there. Same idea here. It's a little bit dicey over here. So I'm finding the area of those 4 trapezoids and adding them all together. So, what's the area of a trapezoid? Good question. It's not a formula people usually remember. But if we draw the trapezoid like this for a second and call this the height and this the first base and this the second base, then the area of the trapezoid is equal to, I like to think of it as the height times the average of the bases. That's how I usually imagine it. And it does work, right? If you take the average of the bases, which is kind of like halfway between this length and this length, looks like about like, I don't know, right there. And if you cut that little triangle off there and put it right there, you get a rectangle whose height is h and whose length is the average of the bases, which is the area of that and that. So it totally works out. So in this imagining, these vertical lines are the bases and the height is the bottom part here, which is kind of an unfortunate naming thing, but oh well. So to find the area of my trapezoids, or I should say my 4 trapezoids, let's write it down. So the first trapezoid is going to have an area of the height, which is 1/2, times the average of the bases. So my average of my bases is going to be f of 1 plus f of 3/2 divided by 2. There's my first trapezoid area. Plus, I'm going to do the same thing for the next one. It still has a height of 1/2, and the average of the bases is going to be this plus that divided by 2. So it's going to be f of 3/2 plus f of 2 divided by 2. Plus, same thing here. We're going to do 1/2 times f of 1. Sorry, not f of 1, f of 2 plus f of 5/2 over 2. And then finally, for the last trapezoid, it's going to be 1/2 times f of 5/2 plus f of 3 all over 2. So pulling this all, so simplifying this a bit so it's not so gross to write, I can factor out a 1/2 and a 1/2. So I can factor out this 1/2 from each of them and also that 1/2 from each of them. So I'm going to write this as 1/2 times 1/2. And now look what's left. I have an f of 1 plus f of 3/2 plus another f of 3/2. So I have 2 times f of 3/2 plus f of 2 plus f of 2. So 2 times f of 2. F of 5/2 plus f of 5/2 is 2 times f of 5/2. Then lastly, f of 3. So then we could say that in this particular example, the integral from 1 to 3 of 1 over x dx is approximately equal to 1/4 times f of 1, which is 1, plus 2 times f of 3/2, which is going to be 2 times 2/3, plus 2 times f of 2, which is 2 times 1/2. 2 times f of 5/2 is 2 times 2/5, and f of 3 is 1/3. And then I would use a calculator because I'm not actually in the calculator, which always feels like it defeats the purpose, right? If you're using a calculator to calculate this approximation, you might as well just use the calculator to approximate the thing in the first place. But I digress. Using a calculator, we would get approximately 1.1167, which is not too far from our actual value of approximately 1.089986. Yeah. So the question here, or I should say not the question here, but I should point out that the trapezoid rule in general has this pattern of paper here. So the trapezoid rule to estimate the area under y equal to f of x on the interval from a to b using n trapezoids works out the following way. So it's always going to be 1/2 times your delta x times, and here's the pattern that I always remember. It's a 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1 pattern, meaning your n's are both coefficients of 1 and everything in the middle has a coefficient of 2. So it's going to be 1 times f of x sub 0 plus 2 times f of x sub 1 plus 2 times f of x sub 2 plus 2's for as long as you need them, all the way up to the second to last term, which is f of x sub n minus 1. And then finally at the very end, a 1 times f of x sub n. Where it's the usual kind of partition of a to b that we've done in the past. Right, so just to fully say, right, you're going from a to b and you're breaking it up into n subintervals. Right, a is equal to x sub 0. And then there's your first x sub 1, x sub 2, x sub 3, x sub 4, all the way to the second to last one is x sub n minus 1, and b is equal to x sub n. And each subinterval has a width of delta x, which is equal to b minus a divided by n. So that's what's kind of going on here. So we're saying, oh yeah, I'm taking this width, and then I'm doing 1/2 f of x sub 0 plus f of x sub 1. There's your f of x sub 0. There's one of your f of x sub 1s. And then for the next one, 1/2 times your f of x sub 1 plus f of x sub 2. So that's why we're getting 2 of everything except for the very ends, because you're adding it here and here, here and here. Each endpoint gets caught up in 2 different trapezoids. Cool. So yeah, that looks all right. Going back to this previous example for just 1 second. So in the previous example, the error in our estimate is the difference between the actual value and the approximate value. So our error is, we usually use a capital E, and we've put some absolute values around our exact value minus the approximate value, which is going to be, in this case, the absolute value of 1.0986 minus 1.1167. Yes, I recognize that these are both approximations themselves, so okay. But if you get this, it's approximately equal to 0.0181. So good, our estimate's pretty good. We're not off by that much. But the whole point of this process is that we usually don't know what the integral is actually equal to. So we won't actually be able to calculate the error exactly, because if we could, then we would have known what the value was in the first place. So the question then becomes, how do we know how good our approximation is? How do we determine how good our approximation actually is. Well, fortunately, there's an error formula. So using for the trapezoid rule, the error, which we write as capital E sub t, the error is always less than or equal to the following sum, or the following, sorry, not the third word, the following value. It's going to be b minus a cubed divided by 12n squared times the maximum of the absolute value of the second derivative of the function over the interval between a and b. So that is the error estimate for the trapezoid. We're not actually going to know what the error is equal to, but we're going to say, well, it's less than or equal to whatever gross number that happens to be. So let's do it for this previous example and talk about kind of what we do. So let's use the error estimate above to, I wouldn't say that we're approximating the error, we're actually getting a bound on the error. The error in trapezoid approximation. So I'll remind you, we calculated that the integral from 1 to 3 of 1 over x dx in our approximation, which was T4, was about 1 point, it was 1167, I think. Yeah. So in this problem, our A is equal to 1, our B is equal to 3, our N was equal to 4. And our f of x is the function we're integrating, which is 1 over x. So the hardest part of this upper bound for the error is dealing with the maximum of the absolute value of the second derivative. Right? B minus a cubed over 12n squared is whatever. But let's deal with this. So our function is x to the negative first. Its derivative is negative x to the negative second. And its derivative is positive 2x to the negative third. 2 over x cubed. So the question then becomes, what is the maximum value of 2 over x cubed when x is between 1 and 3? Sometimes this is easy, sometimes this is hard. In this example, it's relatively easy because 2 over x cubed gets smaller and smaller and smaller as x gets larger and larger and larger. So we know this is going to be maximized when x is equal to 1. So let x equal 1, and then f double prime of 1 is equal to 2 over 1, which is 2. And any other value of x between 1 and 3 would produce a smaller result. So now we can actually calculate the upper bound on the error here and say, well, the absolute value of the trapezoid error is going to be less than or equal to 3 minus 1 cubed over 12 times 4 squared times the maximum of the absolute value of the second derivative, which we just said was 2. And then simplifying that, we get 2 cubed, which is 8 times 2 over 12 times 16. But 8 times 2 is 16, so the 16s cancel, and we're left with 1 over 12, which is approximately 0.0833 forever and ever. So what we're saying is, whatever our approximation is, in this case 1.1167, it's within that much of the actual value, which we know is true because we saw that the actual value of our integral was 1.0986 approximately. And our error is certainly much less than 0.0833. Our error was about 0.018. So actual error of approximately 0.018 is certainly less than this upper bound. 0.083. So that's the whole idea, is that the upper bound here just says, whatever your error happens to be, it's less than that number there. Cool. Question so far? So Simpson's rule is just another way of doing this, which is a little bit more complicated, but gives a better approximation. So let's look at that. Simpson's rule is another more complex way of approximating the area under a curve. So let's look at this example, which again is not going to be very kind of interesting numerically. But let's say we have the function f of x equal to x squared plus x plus 1 on the interval from 0 to 4. And we're just going to use it. We're going to use using n equal to 2 subintervals. Here's what this kind of looks like. Kind of like that. And from 0 to 4. I'm breaking it up into 2 subintervals, so each subinterval is going to have a width of 2. So the difference between, well, Simpson's rule, instead of using trapezoids, you're actually kind of using approximating parabolas everywhere. So what you're really doing to approximate the area under this curve, which happens to be a parabola, is you're using the same parabola through those 3 points. And it is true that any 3 non-collinear points, you can find a parabola that goes through them. So for these 3 points here, there is a parabola that goes through them. It happens to be the parabola that we're already using, which means that the approximation we get here should actually give us the exact value under the curve, which is interesting. Let's see if that happens. Well, so here's what Simpson's rule says. Simpson's rule says, and I'm going to write the general formula first, then we'll do it for this one, is that if you have using Simpson's rule using n subintervals, it's going to be equal to your delta x divided by 3 times f of x sub 0 plus 4 times f of x sub 1 plus 2 times f of x sub 2 plus 4 times f of x sub 3. And it continues on in this 4, 2, 4, 2, 4, 2, 4, 2 pattern. And then at the very end, it ends with a 4 and then a 1. I should say a 2, then a 4, then a 1. So it's 4x3 plus 2 f of x4 plus dot, 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 all the way to the second to last term is going to be 2 times f of x sub n minus 2. The third to last term. The second to last term is going to be 4 times f of x sub n minus 1. Finally, the last term is going to be 1 times f of x sub n. So trapezoid rule, the pattern is delta x over 2, 1, 2, 2, 2, 2, 2, 2, 2, 2, 1. For Simpson's rule, the pattern is delta x over 3, and then it's 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. So in this case, we don't get any 2s because the pattern is going to be 1, 4, 1 because we only have 3 points to deal with here. So our approximating area is going to be my delta x, which is 2 divided by 3. And then it's going to be 1 times f of 0 plus 4 times f of 2 plus 1 times f of 4. Which is then going to equal 2/3 times f of 0 is 1. Plus 4 times f of 2 is, let's see, f of 2 is going to be u2. 4 plus 2 plus 1, which is 7. And then f of 4 is going to be 4 squared is 16 plus 4 plus 1 is 21. So calculating this, we get 2/3 times 1 plus 28 plus 21, which is going to be 50. So 2/3 times 50 is 100 thirds. And it's just kind of interesting that Simpson's rule actually exactly calculates this area correctly. If we actually did the integral from 0 to 4 of x squared plus x plus 1, we would get x cubed over 3 plus x squared over 2 plus x from 0 to 4. And if we plug that in, we're going to get 64 over 3 plus 16 over 2, which is 8 plus 4. 8 plus 4 is 12. And 64 over 3 plus 12. Well, 12 times 3 over 3 is 36 over 3. And oh, look, those are the same. So this is just kind of a unique thing about Simpson's rule, that if you were to use Simpson's rule to approximate the area under a quadratic or even a cubic function, it actually ends up being exact. You wouldn't actually use Simpson's rule to do this, but it does do this if you do it that way. It's kind of weird. Yeah. Do I have what? Yes, I have students on Zoom. Good question. Let's see. How many people are on Zoom right now? I have, let's see, it's hard to see. 3? Up 5. What's that? Sure. So let's use Simpson's rule for something that is a little bit more sensitive. So we're going to go back to the same example as before. So we're going to approximate the integral from 1 to 3 of 1 over x dx with Simpson's rule and n equal to 4. So here's the idea. My picture might get a little bit wild here. So same function, y equals 1 over x. Oh, sorry about that. Thank you. So same function, y equal to 1 over x. And then we're still breaking up the interval from 1 to 3 into 4 equal subintervals. So here's the idea. My picture might start to look kind of crazy here. So using the first 3 points, the idea, and you don't have to know this to calculate it, but the idea is that we're drawing a parabola that goes through those 3 points. I don't know exactly what it looks like, but I know because it's been proven that you can always find a parabola that goes through any 3 non-collinear points. So there's some parabola, maybe it looks vaguely like this. So that parabola, we're going to find the area under that parabola between 1 and 2. And then similarly, for the next 3 points, so we move over, so we did these first 2 subintervals, then we're going to use the next 2 subintervals to draw another parabola through those 3 points. Again, it's going to look maybe kind of similar-ish. Come on, maybe. Okay, sure. That's the idea of Simpson's rule, is that you're just using these parabolas. So watch this. It's going to equal, oh, that's kind of well like that, yeah. So we're going to say that the integral from 1 to 3 of 1 over x dx, I'm actually going to use the previous formula. So I'm not going to jump straight to the formula I knew. It's going to be the following. It's going to be my delta x over 3. And then for the first parabola, I'm going to do f of 1 plus 4 times f of 3 halves plus 1 times f of 2. That's for my first parabola. Just like in the previous one, right? I did 1 times f of 0 plus 4 times f of 2 plus 1 times f of 4. And then for my second parabola, I'm going to do the same thing. I'm going to do, now it's going to be f of 2 plus 4 times f of 5 halves plus 1 times f of 3. But look, if we combine like terms, the f of 2 here and the f of 2 here combine to equal 2 times f of 2. So we get that pattern that I was speaking to earlier, which is this is going to be delta x over 3 times f of the first x value plus 4 times f of the next x value plus 2 times f of 2 plus 4 times f of 5 halves plus 1 times f of 3. And if there had been like another parabola we were adding on there, we would have gotten the 2 times f of 3 plus 4 times f of the next thing plus 1, right? So it's always going to be this 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1 pattern. And then it's still terrible to calculate. This is going to be equal to, so my delta x is 1/2. So 1/2 over 3 times f of 1 is 1. 4 times f of 3 halves is 4 times 2/3. I'm just taking the reciprocal of my values because my function is 1 over x. And then we get 2 times 1/2 plus 4 times 2/5 plus 1 times 1/3. And that's approximately equal to 1.1000. And then just to compare, like we were last time, the actual error is, well, my actual value was 1. Well, I can't remember this number for the life of me. 1.0986 minus our estimate, which is 1.1000, and that's approximately equal to 0.0014. Which, if you remember what our error was for the trapezoid method, our error was 0.018. So this is much better than the trapezoid error, which was equal to 0.018. Right? We're a whole 10 times better. We're a whole order of magnitude better. So Simpson's rule generally gives a better estimate, but it is clearly more work to compute. And then in a similar way, there is an error formula for bounding the error for Simpson's rule. So to bound the error using Simpson's rule, it's a similar looking formula. Instead of the magnitude, or so the absolute value of the trapezoid error being less than or equal to b minus a cubed over 12n squared times the maximum of the absolute value of the second derivative of f, where x is between a and b, it's going to be the absolute value of the error using Simpson's rule is less than or equal to b minus a to the 5th over 180n to the 4th times the maximum of the absolute value of the 4th derivative of x, where x is still between a and b. When I kind of think about Simpson's rule versus the trapezoid rule, I kind of think of everything as bumping up 2 levels. Instead of b minus a to the 3rd, we have b minus a to the 5th. Instead of n squared, we have n to the 4th. Instead of the second derivative, we have the 4th derivative. So everything's kind of increased. But yeah, that doesn't work for the 12 and the 180. Okay, but like other than that. So here we could say that the error using Simpson's rule is going to be less than or equal to, again, for our integral, which was the integral from 1 to 3 of 1 over x dx. It's going to be less than or equal to 3 minus 1 to the 5th over 180 times 4 to the 4th times, we should figure out what the maximum of the 4th derivative is on this interval. So we saw last time that the second derivative was equal to 2x to the negative 3rd. The 3rd derivative is going to be negative 6x to the negative 4th, and the 4th derivative is going to equal positive 24x to the negative 5th, which is 24 over x to the 5th. And fortunately, just like last time, if x is between 3 and 1 or 1 and 3, this quantity is going to be maximized when x is equal to 1. So the maximum value of the fourth derivative of f when x is between 1 and 3 is going to equal 24 over 1 to the fifth, which is just 24. Any other value of x between 1 and 3 is going to yield a smaller result. So that's going to be a 24 right there. And then that ends up equaling something terrible like, I mean, I guess we could simplify it if we want to. That's going to be 2 to the fifth over 180 times 4 to the fourth times 24. Approximately 0.0167. I think it's like, I should know what that fraction is. I don't recognize it off the top of my head, but so, yeah. Which is certainly, that's the upper bound for our error. And as a reminder, our error was actually much less than that. Our error was 0.010014. I will point out the upper bound on the error for the Simpson's rule is a smaller number than the actual error we got for the trapezoid rule. So Simpson's method does really yield a better approximation. The question becomes, do we care enough to do the more work to actually get the better estimate? And sometimes. So these ones are a little, they feel like we're kind of moving backwards in some ways. Like, to me, this feels like, why would you do this? Well, it actually is important. This function in particular, the integral of e to the negative x squared dx, is super important in statistics because that function, f of x equal to e to the negative x squared with some adjustments, is the bell-shaped curve. This is your normal distribution. It looks something like this. And we really, really, really care about how much area is under that curve between 2 points, because that's how you calculate the probability of being so many standard deviations away from the mean. And so, since we can't anti-differentiate this function, we do actually use these approximations to figure out approximately how much area is under the curve so that we can do these sort of things. It's kind of neat. But again, those examples don't lend themselves very easily to being done by hand in class. So I will probably do some different examples here. Let's look at, so one more thing with this last example. Sorry, I forgot there was one more thing. I like this question a lot. So the question we ask sometimes is, for that previous integral, from 1 to 3 of 1 over x dx, how large should n be so that the estimate using the trapezoid rule is accurate to within 1/10,000. So the question that we're really asking is, how big does n have to be so that the upper bound for the error is less than that number? So find n so that the error using the trapezoid method, which is less than or equal to 3 minus 1, 3 minus 1 to the third over 12n squared times the maximum of the second derivative, which we found before to be 2. That's the max of the absolute value of f double prime. We want that to be less than 1 over 10,000. And so our job here is to solve for n, which isn't too bad. So looking at this here, simplifying the left-hand side, we have 2 cubed, which is 8 times 2, divided by 12n squared. is less than 1 over 10,000. My usual go-to move is to cross multiply and say, great. On the left, I have 16 times 10,000. Right, multiply there is less than 12n squared. Although really I could have left the 12 on the left-hand side in the denominator. So what I really have here is that n squared should be bigger than 16 times 10,000, which is 160,000 divided by 12. Then I need a calculator, so 160,000 divided by 12 is approximately 13,333. So we want n squared to be bigger than 13,333, or n to be bigger than the square root of that, which is approximately, square root button's over here. I don't recommend the phone calculator. It's about 115.47. So here's an important question. Do we round up or do we round down? Well, you might incorrectly think we round down because 115.47 is closer to 115. But the problem is n has to be bigger than that number. So if you say it's 115, well, maybe you're missing it by just a little bit because maybe n needed to be like 115.3. So we always round up. So here we are going to say that n should be at least 116. Okay. We're going to do it again for Simpson's rule because something extra wonky happens with Simpson's rule. So same question for the integral from 1 to 3 of 1 over x dx. Now how large should n be? So that the estimate using Simpson's rule is accurate to within the same threshold, 1/10,000. I will point out, we should expect n to be a much smaller number here because Simpson's rule gives a better estimate. So we shouldn't need to use as many subintervals to get just as good an estimate using Simpson's rule versus using the trapezoid rule. Same process. So we want to find n so that our error using Simpson's rule, which is already less than or equal to b minus a to the 5th over 180 times n to the 4th times the maximum of the opposite value of the 4th derivative, which we found to be 24 last time. It's the maximum of the absolute value of the 4th derivative of x, where x is between 1 and 3. We want that to be less than 1 over 10,000. So we do the same sort of thing. We have on the left-hand side, 3 minus 1, which is 2 to the 5th times 24 over 180 times n to the 4th, less than 1 over 10,000. And I guess I'll try to be a little bit smarter this time. I'm going to kind of cross multiply. I'm going to multiply both sides by 10,000 and get 10,000 times 2 to the 5th is 32 times 24. But I'm going to leave the 180 in the denominator there. And then I'm also going to multiply both sides by n to the 4th and say that's less than n to the 4th. So then what we're going to get is n should be bigger than the 4th root of 10,000 times 32 times 24 over whatever, 180. So this is approximately equal to 14.37. So here's the weird news. We're going to round up. You know, we're going to round up to 16. Why 16? Why not 15? Well, when you use Simpson's rule, n has to be even. So, right, if you look back at the idea here, and I know I didn't say this very explicitly when we were doing it, but whenever you're doing this, I had to have 4 subintervals here so that I could use the first 2 for my first parabola and the next 2 for my next parabola. So I always have to have an even number of subintervals so that I can always have 2 of them to go for each parabola I'm drawing. So teachers love this question. They love making it so when you're approximating this, n has to be slightly bigger than an already even number. So then you don't just bump it up to 15, you have to bump it up all the way to the next even number, which is 16. So just be a little careful if you see a problem like that. Okay. How much time? Okay, we got time. So those problems both had the advantage of it was relatively easy to maximize the absolute value of either the second or the fourth derivative. Let's look at another example where it's a little bit more challenging. So let's say we want to find n so that the trapezoid estimate of an integral that we actually can't do, of the integral from 2 to 8 of 1 over the natural log of x dx, is accurate to within 10 to the negative third, which I would always rewrite as a fraction 1 over 10 to the third, which is 1 over 1,000. Much of the time, your teachers will give you these formulas on the exam, but you should definitely make sure you memorize this formula if that is expected of you. I don't think it'll be expected of you, but you should ask your professor, or your professor should say. So here, the error using the trapezoid method, we know is going to be less than or equal to, do we know the formula? I know the formula. Yeah, it's b minus a cubed over 12n squared times the max of the absolute value of f double prime of x. And we want that to be less than 1 over 1,000. That's our job. So we know everything. Well, we don't know n, but we know b, we know a, and we're going to find the maximum f double prime. Ooh, f double prime is going to be a little bit funky here. So let's figure that out first. So f of x is 1 over the natural log of x. I think I'd rather not use the quotient rule. So I'm going to rewrite that as the natural log of x in parentheses raised to the negative 1 power. And then we're going to find the second derivative, which is, it's going to be a little bit gnarly. The first derivative is going to be negative 1 times the natural log of x to the negative second power times the derivative of the inside, which is 1 over x. And then we're going to, how am I going to think about it? Yeah. So then we're going to take the second derivative. We're going to use the product rule. So I'm going to think of this first piece as my f, that second piece as my g. So then my second derivative here is going to be, so f prime is going to be negative 1 times negative 2, so 2 times the natural log of x to the negative third times 1 over x again because of the chain rule. There's my capital F prime times g, which is 1 over x. Plus, then we switch it up. It's going to be negative 1 times the natural log of x to the negative second times the derivative of 1 over x, which is the derivative of x to the negative 1, which is negative 1 over x squared. There's my f times g prime. Okay, this looks kind of gross. It might have been better to have done this using the quotient rule in the first place. Oh well, sometimes you make the wrong choice when you're doing problems like this. So, okay. Yeah. Quotient rule probably would have been better. So let's simplify this. I'm gonna need a common denominator. I'm gonna rewrite this as 2 over x times x is x squared, natural log of x to the positive third. And this one here is going to be minus a minus, so plus. I have a x squared, and I have a natural log of x squared on the bottom. Well, it's actually pretty easy to fix. All I'm going to have to do is multiply this second piece by, well, not fix. Pretty easy to get the common denominator for. I have to multiply this second fraction by the natural log of x over the natural log of x. So this is equal to 2 plus the natural log of x over x squared times the natural log of x squared. Okay. So now here's the question. How big can this be? Well, here's what we don't want to do. Normally, you would say, well, I can maximize the function by taking its derivative, setting it equal to 0, and finding a critical point. It's going to be really awful. What we should do is just kind of wing it, for lack of a better word. We're just going to kind of make our best guess by doing a few kind of not super kosher things, but things that are totally allowed and everyone does. So here's the idea. We want to make 2 plus natural log of x over x squared times the natural log of x cubed. That should be cubed, not squared. Sorry about that. As big as possible, where we are limited by the fact that x has to be between 2 and 8. The general idea is that you pick whatever values of x you want to make each part as big as possible, to make the whole thing as big as possible. And in a fraction, that means making the numerator as large as possible and making the denominator as small as possible. So we're going to say that this for sure is going to be less than or equal to. So pick the largest value of x for the numerator, so 8. Pick the smallest value of x for the denominator, so 2 squared times the natural log of 2 cubed. And if you plug this into a calculator, because you kind of have to use a calculator here, this is going to be approximately equal to 3.06. It's too bad it's not less than 3. I don't really want to jump up to 4 here. So that's what we're going to use. It's not great, but it's fine. So this is a totally okay thing, right? I'll show you another example in a minute where we kind of do the same thing, but it's really, really fine to say, I'm just going to pick whatever x makes the numerator the biggest and whatever potentially different value of x that makes the numerator the smallest, because that's going to make the fraction as large as possible. All right, so then we're back to this, right? We were in the situation here. We wanted to figure out what was going on with this. And now we're going to say that we have b minus a, so 8 minus 2 cubed over 12n squared times the maximum of the opposite value of the second derivative, which we just found to be 3.06. And we want that to be less than 1/1000. It's totally fine that this maximum is too big, right? The actual maximum of that second derivative is almost definitely smaller than that, but we don't really care. So then we're going to solve for n, same sort of deal. I have 6 cubed times 3.06 divided by 12 on the left. I'm going to multiply by 1,000 on both sides. I'm going to multiply by n squared on both sides. So then we get that, all right, this is, I believe, well, I don't even really care. We're going to get that n needs to be bigger than the square root of all of this. You will need to use a calculator at some point for most of these problems, or be given some very, very nice numbers. This ends up being approximately 235.7. So since it's the trapezoid rule, we're going to round up just to the next integer. It doesn't matter if it's even or odd. It happens to be even here. So we need n to be bigger than or equal to 236. Okay, we'll do one more. One more, yeah. And then we'll talk about the other thing that I can't think of the name of right now, but we'll definitely find out in a second. Parametric curves. So let's do one more of these finding n things, which is the following. So we're going to find n so that, yeah, we'll do trapezoid again. The trapezoid estimate of the interval from 0 to 1 of sine of x squared dx is accurate to within 10 to the negative fourth, which is 1 over 10 to the fourth, which is just a 1 followed by 4 zeros. Just like the previous example, sine of x squared is a function that cannot be anti-differentiated, or it just can't be done. So We are going to do what we did before. We're going to say that the error using the trapezoid method should be less than or equal to b minus a cubed over 12n squared times the max of the absolute value of the second derivative. And we want that to be less than 1 over 10,000. So let's find or approximate the maximum of the absolute value of the second derivative. So my function is sine of x squared. My derivative is cosine of x squared times 2x. My second derivative, product rule, derivative cosine of x squared is negative sine of x squared times 2x times the other 2x plus cosine of x squared times 2. So let's simplify this a tiny bit. This is negative 4x squared times sine of x squared plus 2 times cosine of x squared. All right. So what's the biggest this could be? Well, in fact, so if I take the absolute value of f double prime of x, which is the absolute value of negative 4x squared sine of x squared plus 2 cosine of x squared. There's something really, really lovely about sine and cosine. Sine and cosine are always, always, always going to be less than or equal to 1 and bigger than or equal to negative 1. So it's always true that sine of anything is between negative 1 and 1, and cosine of anything is between negative 1 and 1. So we want this part to be as big as possible and this part to be as big as possible. I'm going to pick x equal to 1 here. And I'm going to make sine, I'm going to say that sine could be negative 1. So I'm trying to come up with the biggest positive value. So this is for sure going to be less than or equal to negative 4 times 1 squared times negative 1. And I'm going to say cosine could be positive 1 times 1. So this is less than or equal to 4 plus 2, which is 6. Again, it feels a little shady, a little dicey that we're just kind of saying we get what we get, but it's totally fine to say, yeah, this part, no matter what x is, this part's always less than or equal to 4. This part's always less than or equal to 2. And so the sum of them is for sure going to be less than or equal to 6. There is probably a smaller number that is also an upper bound, but 6 is perfectly good. So then we do the usual kind of thing. We're going to say that, great, this b minus a cubed, which is 1 minus 0 cubed over 12 times n squared, times this maximum, which we just said was 6, is less than 1 over 10,000. So what we have here is 10,000. 6 over 12 is just 1/2, so 10,000 over 2 is less than n squared. So n should be bigger than the square root of 5,000. And that ends up being approximately, well, n is bigger than 70.7. So n should be bigger than or equal to 71. Because again, for trapezoid, we don't care if it's odd or even. For Simpsons, it has to be even. All right. So Simpson's rule, trapezoid rule is a lot of plugging into formulas and just getting answers that are kind of numerically gross, but fine. Let's look at something completely different. Parametric equation. My last name has often been mistaken for a parameter, and is in fact parameter. But that's neither here nor there. So a parametric equation is just a way of defining a curve in space in terms of a third parameter. So for example, you could have x equal to t plus 2 and y equal to t squared. And we could limit t or not. Sometimes t goes across all real numbers. Sometimes we say, oh, let's stick to t being between like -2 and +3. We could certainly try to figure out what's going on by plotting some points. So we pick some t values and some x and some y values. So let's start at the lower end of t being -2. Let's just plug in all of the nice integer values from -2 to +3. So if x is equal to t plus 2, then x is always going to be 2 larger than t. So -2 plus 2 is 0, and then 1, and then 2, and then 3, and then 4, and then 5. Y equals t squared. So if t is -2, y is going to be 4. -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. If we're going to graph this, we're only going to plot the x and y coordinates. T actually doesn't get graphed. So here, we're starting at the point 0, 4. And then we're going to get the point 1, 1. And then the point 2, 0. And then the point 3, 1. And then the point 4, 4. And then the point 5, 9. And it looks like a portion of your usual parabola. Well, your usual parabola is shifted. Sorry. Often with parametric curves, we do draw little arrows to indicate the direction that t is increasing. So if over here is where t is equal to -2, and here's t equal to 0, and here's t equal to 2, and here's t equal to 3, we are traveling in this direction, where essentially from left to right. That's not always going to be true, but we always will travel in the direction of t increasing. So this seems like a lot of work. We don't always want to do this. In fact, I would rather not graph this way unless I really, really had to. So what we often like to do is we try to, if possible, eliminate the parameter, which is usually t, but you can use lots of other things. Theta is also often a parameter to help us graph it. So usually what that means is taking one of these two equations and then isolating t. And we try to pick the one that's easier. So looking at these, I'd rather not take a square root of both sides. So I'm going to use x equals t plus 2 to isolate t. So x equals t plus 2 becomes x minus 2 equal to t. And then I'm going to substitute that expression for t into the other parametric equation. So y equals t squared is going to become y equal to x minus 2 squared. Which is what oh, I forgot to plug in my laptop. Let me go ahead and plug it in before it dies. That'd be terrible. It's a race against time. Cool. Okay, safe. So this parabola certainly looks like your parabola y equals x minus 2 squared. It's your usual y equals x squared shifted 2 to the right, which is exactly where we ended up. We do have limits or bounds on what x can be. So if t is between -2 and 3, then t plus 2, which is what x is equal to, well, if I add 2 to everything, -2 plus 2 is less than or equal to t plus 2 is less than or equal to 3 plus 2. So 0 is less than or equal to x is less than or equal to 5. So we could have graphed this by saying it's y equal to x minus 2 squared, where x is between 0 and 5, which is exactly this graph right here. So that is often how we deal with sketching a parametric curve without trying to plot a bunch of points. Let's look at another example. Yeah. Let's say we wanted to graph the curve defined parametrically by parametrically, how do you spell parametrically? By x equal to e to the t and y equal to e to the 3t. And no, I'm not going to say that. Gross. I don't want to plot points here. Because if I did, it's going to be really challenging. Right? If I plot like t and x and y, I can think of one good value of t, 0. And then x is going to be e to the 0, and y is going to be e to the 0. But then at any other point is going to be not nice. If t is 1, x is going to be e to the 1, y is going to be e to the 3rd. And it just gets worse and worse if I keep picking values of e squared, e to the 6th. Like, I don't really find that helpful. So we're going to do the thing we said we should, which is we're going to try to write y in terms of x. We're going to try to eliminate t. And in this one, I would say there's 2 valid ways you could do this. One way is just kind of seeing it. So you might be like, oh, wait a minute, James. If you look at y equal e to the 3t, that's really equal to e to the t cubed. But then x is equal to e to the t. So we can replace the e to the t there with x cubed, with x, and get x cubed. So one way to eliminate t is that way. It's kind of just by seeing what happens. But that's not very algorithmic, right? Like it's just kind of like, oh, I saw a thing, it worked. The more kind of thing that works every time, or at least that we should try every time, is first to solve for t. In either equation, I'm going to pick the one that looks quote unquote easier. To me, that's the x equals e to the t. So if x equals e to the t, I can take the natural log of both sides to get t equal to the natural log of x. And then I can take the other equation, y equals e to the 3t, and replace the t with natural log of x. So that then y is equal to e to the 3 natural log of x. Now we do have to be able to simplify this to make it look reasonable. That 3 gets to come up as the power. So I can write this as y equal to e to the natural log of x cubed. And then e to the something and the natural log of something undo each other, and we just get y equal to x cubed, which is perfectly fine. So let's graph this. And here's where things get a little bit funky. If we graph this, we're not going to get the entire graph of y equals x to the 3rd. And here's why. So we're going to graph y equals x to the 3rd, but we have to remember that x is really equal to e to the t. And even if t gets to be everything from negative infinity to infinity, e to the t is always non-negative. In fact, it's always positive. So x equal to e to the t is going to be greater than 0 for all values of t. So normally, if I was just going to graph y equals x cubed, I would get the graph of y equals x cubed, which looks kind of like this. It's not my best. Close enough. But what we should actually be getting here is something slightly different. If we're graphing the parametric equations x equals e to the t and y equals e to the 3t, it's going to look like a portion of that, except we know that x has to be greater than 0. So when we graph this, it's going to be the portion of this graph where x is greater than 0. So it's going to start, well, it's going to start not quite at the origin, and then it's going to do the usual kind of shape. So that's what the graph looks like. You get point 1, 1, you get point 2, 8, and so on and so on and so on. But it's just that portion of the graph of y equals x cubed, which is a little strange. And if we had decided to limit t, so for example, if we had instead said same graph, we're going to graph x equals e to the t and y equals e to the 3t, but then we're going to limit t to being positive, or I should say non-negative because I say greater than or equal to 0. Then we would get the same graph, except now the smallest x could be would be e to the 0, which is 1. So we'd actually be starting at the point 1, 1 and getting just that portion of the graph. So here's t equal to 0. Here's t equal to 1, and so on and so on and so on. Over here, here's t equal to 0. Here's t equal to the natural log of 2, because that's what I happened to pick there. And over this way is t getting super duper negative. So right there is t going towards negative infinity. It's kind of interesting. So these parametric curves can be a little bit strange in that you might think you get something that looks like a normal graph, but is limited. Another easy example of this is something like if I wanted to graph the parametric curve x equal to cosine of square root of t and y equal to cosine of t. And in this case, I would actually, well, I really wouldn't solve for t at all. I would just say, I'm going to use the y equal to cosine t instead of the x equal to cosine square t. And I'm going to see that x is equal to cosine of t squared. And then I can sub in y for cosine and get x equal to y squared. And I'm going to say that t can be anything. T goes from negative infinity to infinity. Normally, the graph of this would look like a rightward opening parabola that is that. But that's not our graph because we're limited. The biggest cosine can ever be is positive 1. The smallest cosine can ever be is negative 1. So our actual graph is very, very limited. We're only going to get this portion of the parabola. And it actually kind of goes back and forth. So, right, cosine of 0 is equal to 1. So we start here at t equals 0. And then if we go to time equal to, say, pi over 2, cosine of pi over 2 is 0, cosine of pi over 2 is 0. And then over here, if we go to time equal to pi, cosine of pi is negative 1, but cosine squared of pi is positive 1. And then if we let time keep going forward, then we're going to end up going back the other direction. So this is also going to be 3 pi over 2. This is also going to be 2 pi. And we just kind of keep going back and forth this way, and then back the other way, and so on and so on and so on. So you just keep going back and forth and back and forth and back and forth forever and ever. Let's do one more and then we'll call it a day. So these are moderately useful things I've said, but the next thing I think is actually you will use in 21C. So let's find a parameterization for the following curve. So the line segment from the point 4, -1 to the point 1, 7. So we're looking at something like the line segment that starts here at this point and ends here at this point. Whoa, can I draw it? Maybe. So I'm imagining that we're starting it, and it's very convenient to start at time equals 0, although you could make any choice. And it's also very convenient to end at time equals 1. And that's the point 4, -1. That's the point 1, +7. So we need to find parametric equations for x and y. which people might write as x of t and y of t. Either way is fine. So here's how I'm thinking about this. At time equals 0, x should be 4. So I'm going to have a 4, and similarly, at time equals 0, y should be negative. And then I'm going to add some multiple of t. So if t increases by 1, I need x to go from positive 4 to positive 1. So x is going to decrease by 3. So what I need is a negative 3 times t. Let's check that out. If time is 0, x of 0 is going to be 4 plus 0, which is 4. If time is 1, x of 1 is going to be 4 plus negative 3 times 1, which is 4 minus 3, which is 1, which is what we get there. Similarly, from time equals 0 to time equals 1, y is going to increase from negative 1 to 7, so it's going to increase by 8. So I need to add on 8 times t. So that, again, if you plug in 0 for t, y of 0 is equal to negative 1. Plug in 1 for t, y of 1 is equal to negative 1 plus 8, which is positive 7. So that's a very kind of common thing we do if we want to draw or parameterize a line segment, is we start off with x and y equal to whatever their initial values are, and then we add on the difference from their initial to their terminal multiplied by t. In a very similar way, we can do the same thing for the line segment from 5, 3 to 9, negative 4. You say, well, great. I know that x is going to equal the initial value when time is equal to 0. And then we're going to add on the difference. So the difference between 5 and 9 is positive 4 times t. And similarly, y should be the initial value of y, which is 3. And then we're going to add on the difference to get from negative 3 to to get from positive 3 to negative 4, we subtract 7. So it's going to be plus a negative 7 times t. And we do use this technique relatively frequently in future classes. All right. I think that's enough for today. We'll continue talking about parameterizations and then polar coordinates next week. As a reminder, I know we don't meet on Mondays, but your classes don't meet next Monday because it's Memorial Day. So don't come to class on Monday. We won't be here. You shouldn't be either. That's all I got. Have a lovely rest of your day.